Okay, so we have the two conformations of ethane eclipsed, where the H's are aligned with each other, and the staggered conformation where they're not. They're as far apart as possible. And there's a slight repulsion between the CH bonds. You should have seen this in Gen Chem with bonds around an atom, or electron pairs around an atom repel one another. And we have a similar effect, even though they're not on the same atom, I guess, going on here between all the CH bonds. They're repelling one another, so if we look at staggered form, this is repelling this, this is repelling this, this is repelling this. And if they're aligned, that's going to be at a maximum. Any way we go, we're going to reduce that slightly. So this is tending to make the eclipse form less stable. Meanwhile, staggered form, if we rotate it to the staggered form, now we have we've minimized that repulsion, because this is further away from this, this is further away from this, etc. So we've more or less reduced it as far as we can. It's not eliminated entirely, but it's the lowest it can possibly be unless we take the whole of ethane apart. So let me summarize that on the board. And we call this torsional strain. And we often refer generally as these sorts of effects relate to the bonds and atoms getting closer together than they would like to be. We often refer to this type of interaction as a steric interaction. So these bonds would rather stay further apart. If we try and push them together, there's a slight steric strain or torsional strain in the molecule. Now, if we look at the how the energy changes, you can see that ethane is not going to rotate freely, well, this doesn't rotate freely either, as you can see here, but you would think if you make it this with your model kit, and I encourage you to do this, you can just spin it around freely. But it's not as free as it might look, because every time the H's are aligned with one another, there's a slight hump in the energy barrier, and that's relieved again when we go to the staggered form again. Every time we rotate, energy hump, and then back down into the valley again. So the barrier to rotation is about 3 kilocalories per mole, or about 13 kilojoules per mole. And the book uses kilojoules. That's perhaps what you're more familiar with from Gen Chem. So this is on page 181. Now what means is if we were to go into outer space where it's really cold with a molecule of ethane, it would freeze out in the staggered form and it couldn't rotate anymore. It would stay in this form. Now, we can draw a graph of this, and this is what's on page 181. And I encourage you, if you're drawing your notes, take a look at page 181. You'll get a lot more realistic rendition of the curve, of the energy curve. But I will attempt, in my pathetic way, to try and reproduce it on the board. So, alright, so our scale is going to go up to 15 kilojoules per mole. I'll put the 0 down here. And we're going to put relative energy here. This isn't an absolute energy. And just because it goes eclipsed doesn't mean, just because it goes staggered doesn't mean it has 0 energy. It just means relative to the less stable form it has. We can set this as like sea level if you like. Now sometimes you put a 0 here and go out to 360 degrees. The book prefers to have the 0 in the middle, so I'm going to try that here, if I can draw it. So going to the left, we're going to go to minus 180, and going to the right, we go to plus 180. Now let's set the 0 point, for the sake of argument, with the atoms aligned. Like this. And actually I don't have a coloured structure here, but in my drawing on the board I'm going to label a couple of the hydrogens. I'm going to maybe use blue and red if I can. Alright, that's the energy curve. And at the 0 point I'm going to put one of the staggered forms, and let's just randomly choose to label the front hydrogen as red and the back hydrogen as blue, the ones that are at the top at the start. Now if you choose to rotate this, there are a variety of ways you can do it. You can rotate the front one, you can rotate the back one, whatever you prefer. The book seems to rotate the back one. I kind of like doing that myself. So if we rotate it this way, we get to a staggered form where the blue now is 60 degrees counterclockwise as you're looking at it from the red one. So that's the minus 60 degrees. And we get something like that. So this has gone from an eclipse form down to a staggered form, which is about 13 kilocalories more stable down here. And I'll try and draw the rest. we move to the left, we rotate this way, this way, to get to here. Then we rotate further, so now we get to another eclipse form. Now the blue hydrogen is 120 degrees different from the red one. And then if you keep going, now the red atom and the blue atom are 180 degrees apart. And that's where we've got to here. This one is supposed to refer to the 0 degrees. Now we have an equivalent thing if we try starting at the same 0 point and rotating the back clockwise instead. So I'll draw those up now. Okay, we've now completed the drawing, and hopefully you can see as we rotate this way, we go to a staggered form where now the blue is 60 degrees different, then 120 degrees different, and then 180 degrees different. Now, you may have noticed this one where the blue and the red are 180 degrees apart. This one here is in fact the same as this one here. And that's because these are in fact 360 degrees apart from each other, which means we've come full circle now. So we've now completed the graph, and the conformation I've drawn at this end is the same as this one. So this is what ethane looks like. So as it rotates, it's wanting to go staggered, but it's got enough energy at room temperature that it can keep rotating, but it's not a free rotation. It's jumping over this energy curve as it rotates. So next we're going to start looking at propane, and I'll cover that in Monday's class.